Hi, I'm Jacob Cebulski. In this presentation, we're going to discuss data clustering and segmentation analysis. What you see in front of you is a typical picture that people have in mind when they talk about clustering, when they talk about visualization of clustering results. And this is also the picture which is quite inaccurate and quite useless when it comes to dealing with data clustering. So let's do it differently. Let's talk about a different approach to clustering. First of all, I'm going to give you a brief introduction to what data clustering is all about. We're going to use a data set which is available in Kaggle and which has been described by Dean de Kock in his article published in the Journal of Statistics of Education. The data is available from this link and a brief description of all the fields. The data is about the sales of houses in Ames, Iowa, USA. As a challenge, I also give you a link to a different data set where dealing with the sales of houses is much more difficult. Melbourne real estate data set. So briefly, what's data clustering? It's the unsupervised method of grouping data. So the data points in the same group, called clusters, are more similar to each other than those in other groups. This is quite different from analysis of those clusters, also known as segmentation analysis, which is the process of knowledge discovery, learning about data by interpreting those groups or clusters. Also, I should distinguish those two concepts from cluster diagnostics. Usually it's involved either applying some mathematical concepts and visualizations to assess the quality of the resulting clustering system. So we're going to cover those three concepts, and we will be using a very popular method, especially in R. It's a function called PAM from the popular cluster package. PAM stands for partitioning around Medoids and represents a group of clustering approaches called centroid-based approaches. The approaches which seek a number of data points in the space of your data, and usually that number is predefined, k, and we are going to group the data items around those specific points, which will become the centers of future clusters. The main difference between methods such as k-means and k-Medoid, which PAM is implementing, is that k-means is looking at the centers which are not necessarily the data points. Those centers could be in between the data points. They're calculating as the means of different coordinates or dimensions of the data set. Whereas PAM, it actually selects a specific data point which is closest to the center. And this is also not the same as k-median approach, which uses the median calculations. k-Medoid is trying to optimize some kind of a objective function for the clustering system. It's some kind of a cost function. So k-Medoid and k-median approach are quite different. PAM used to have some bad publicity in the past because it was quite inefficient, but over the last few years, various optimization techniques made it as efficient as k-means. So it is popular and it gives you certain advantages over k-means. It's also more robust. In this presentation, I'm going to focus on two important aspects. First of all, that we want the methods to be robust when dealing with malformed data, such as presence of outliers. And the second issue is that once we develop the clustering system, we want this clustering system to be applicable to new data. You can see a lot of different libraries in R and many other programming languages which offer analysis of clusters, but this analysis is once off. It cannot be applied to new data without going outside that clustering method. So we're going to select methods and approaches which can deal with outliers and malformed data, and which can be applied to new data. And that creates certain challenges in processing. I'm going to use a number of libraries in R. Caret, gplot2. So Caret is actually useful for dealing with pre-processing of data, which creates a model which could later be applied to new data. ggplot for visualization, cluster for clustering and applying PAM method, and also applying different measurements of cluster quality. Factor extra, which provides a lot of visualization functions, especially when dealing with principal component analysis, which will be used in this process. And alluvial, which is very useful for the final interpretation of clusters. I'm using a Jupyter Notebook, which is fantastic for dealing with R. Usually Jupyter Notebook will be available on Kaggle. So if on Kaggle you want to create a kernel, Jupyter Notebook is available for R programming and Python programming. You can install it on your own computer if you wish to, and usually comes with the installation of Python related software environments such as Anaconda. And you could actually extend it to deal with R. I have a sequence of utility functions which are available with this notebook on my GitHub, and links to the GitHub can be found on YouTube description of this video. Search there and you'll find the link there. Those utilities simply hide away the complexity of ggplot, some of the most complex plotting functions which will be used here. The first thing is that I have already split the data available. So if you download the data, it's about 2,930 records, and I split it two ways, for training and then for testing. And the testing will be to basically look at how this model will be applicable to new data. So I'm reading 2,000 observations, which I'm going to deal with here. And the first thing I'm going to do is to move the ID, the unique identifier of houses in Iowa, to be the names of the rows. So as we start manipulating the data, the identifiers will stay preserved. This is what you're going to see. We have numerous real estate properties. There's about over 80 columns. It's actually, I limited to 80. I removed some of the IDs. One of the IDs became the row name. And here we have the zoning information, the area of the frontage of the lot, the area of the whole lot, the type of a street, and so on and so on. Information about bedrooms and levels, garage, years sold, months sold, the type of sale, the condition of the house, and eventually the price. And normally this data set is used to predict the price of houses sold in Ames. We're not going to do that. We're going to try to understand the data. So there's three main aims of data clustering. Number one is to understand the data around the clusters. The second is to use cluster representatives as the new data, and therefore you could reduce the volume of the data significantly. And the third one is that you could basically consider the fuzzy membership of data in clusters, the probability based on distance of data points from the centers. And those probabilities could be used as new variables describing each of those houses, and possibly in many cases they could replace those variables. And if so, you could significantly reduce the dimensionality of data. That means the number of variables describing the data. So we're going to look at the first one, and that means we're going to try to understand the data through the clusters. First of all, many of the centroid-based methods cannot deal with non-numeric data, which is quite obvious. Virtually all of the clustering methods, they require data to be numeric, unless we could apply some mixed measurements or kernel-based methods, or convert categorical variables to dummy variables, and all data has to become numbers. The second condition is that the data usually needs to be standardized, centered, and basically all variables should be within the same scale. This is to assure that we could treat all variables on equal footing. So I'm going to do some pre-processing in this, and the first thing is that I'm going to select all numeric columns only. I could be dealing with dummy variables here, I could do some tricks, I could use kernel methods. For this presentation, let's just look at numerical variables only, and this is already quite complex. There's about 37 variables, and it's quite sufficient to move into clustering. Now, most of those methods will not be able to deal with missing values, and so I'm going to first find how many missing values I have in each of those variables, and I sort all of those variables by degree of missingness in them. And you can see that the lot frontage has about 16% of missing values. The garage, the year built of the garage is about 5%. Everything else is less than 1% of missing data. It's not a lot. If we had something very significantly empty, we would remove such variables altogether. Otherwise, I'm going to apply some imputation method to fill in the missing values with something else. I could be using a predictive methods, but in this case I'm going to use a very simple method of replacing missing values with the median of that column. Note here that I'm using a caret pre-processing method. What it means is that I can create a model based on the data for each of those variables and then apply the model to the data itself, and it will replace missing values in all columns using that model. The good thing is I can save this model for later use and apply it to new data. So that's very convenient, because it's important that in a new data we use exactly the same imputation method, and if it's a median, we want the median to be identical to the median discovered in the training process as the median in the new data, which is unlikely to happen. So let's do this. We can see that the missingness disappeared. We have all data with all values present, which is great, because we cannot actually use data with empty values later on. The second issue is the standardization. I'll make a copy of the data. If in case I make it wrong, I can go back and make suitable corrections. And let's look at current distribution of variables. You can see that some variables, such as the sale price, is dominating all other variables. Then we have lot area, which is equally large, but everything else has been squashed. So what we need to do is to rescale those variables and center them around the mean, so that they are put on equal footing. They will be considered equally important. In this process, often, depending on the method of scaling, some infinities could appear, missing values could appear, so I'm checking that this is not what happened. And again, I'm using a pre-processing method from caret, which creates a model which could be applied to all data to standardize, center and scale the values, which could be used for the new data. And it looks like no missing values have been generated, and the result is a new distribution. In this new distribution, you can see that sale price disappeared as a dominating factor, and the data have been scaled As a result, we have much better distribution, but one in which you have quite a few outliers. There could be a problem for some approaches. We will be using robust approaches which can deal with missing values. You can also see that some of those variables have almost like a little dash. The interquartile range is minimum or possibly 0, and some of the robust methods cannot deal with the interquartile range, which is a single value. Okay, so some variables, possibly due to imputation of missing values, possibly for other reasons, they ended up with interquartile range consisting of very few possible values. I'm going to deal with the following two problems now. Number one is that quite often Medoid-based approaches to clustering and centroid-based approaches, they cannot allow for the variables to be dependent. They want variables to be quite independent. What can we do about that? Okay, one standard method of dealing with variable dependency is use principal component analysis. That means to rotate the existing dimensions, existing coordinate system, which is our variables, into a new coordinate systems where all coordinates of all new variables are orthogonal to each other. And the great thing about PCAs is also identifies the most important variable as number one, the first principal component, and the second most important, the third, and the importance is determined by the amount of variance that each dimension can explain, the variance in the data. So the standard PCA cannot deal with outliers. We have outliers in this data, so we're going to use the robust PCA. There's quite a range of those methods, and unfortunately very few of them can deal with variables where interquartile range is 0. So the first thing is, let's remove them. So I have just removed, I use the IQR function to determine the range of interquartile range for each variable, and you can see that quite a few variables have interquartile range 0, and they will be removed. The ones to be retained are non-zero, a positive range. So we suddenly dropped from 37 variables to 28, and for the purpose of this clustering methods, we're quite comfortable. Now we're going to create the robust principal component analysis model, and again I'm using printcomp. It's a function where normally we would use correlation table to be able to rotate our coordinate system, and instead I'm using the robust covariance. The robust covariance can actually deal with outliers, and the model will be saved, could be applied to this data, but also could be applied to new data in the future. And I'm going to look at the matrix, the first 9 columns of the matrix, the principal components, and this is the matrix which allows us to rotate the original variables into a new variable set, which will be quite meaningless. As you can see here, this is the projection of the old set of variables into the first 2 principal components. So you can see that they all seem to be squashed and close to each other. It's simply a projection of the shape of the original data into the surface of 2 principal components. And this is what the new data looks like. So those are the original row numbers, or our IDs for each houses, and it's quite meaningless as just a set of numbers. But those set of numbers will be useful. You can see there's all numeric, they're all orthogonal, and principal component 1 explains the majority of variance in the data, then principal component 2 and the 28th principal component explains the least, mostly noise. A good thing at this point is to check whether the the scores, that means the data captured in training to create the model and stored within the model, is whether the scores match when we apply the model to the new data, or in this case, whether if we try to predict, that means rotate the data which made the model and create a new data set, whether or not these are identical. You'd be surprised that in many PCA packages this is not so, and it's amazing that you still have to read into it and test it, that the developers never assured that this is a simple way of application of PCA model to new data. Often you need to do a bit of mathematics and learn how exactly the method works before you could apply it. In this case, I'm quite happy. The robust PCA using printcomp can be trusted for the future use. Now we have 28 principal components, and a good question is how much variance, how much richness of the data those principal components explain. You can see here that if we take the first two principal components together using this cumulative variance plot, they explain over 40% of variance in this data set. If you take 5, they explain over 60% of variance in the data set. If you take 20, this is probably around 95% of variance in the data set, which means that the remaining 8, they explain mainly noise. So normally at this point I would drop off some of those variables because they don't help us very much. Mostly possibly outliers are in those 8 components. I'm going to keep it here because it would make this process more complex, but keep it in mind that at this point we could reduce the number of principal components, and also at this point we could possibly remove outliers using one of the global outlier detection methods. And the great thing is that some of those robust PCAs, such as ROS PCA, they can actually not only create the principal components, that means the method of rotating the original variables into new coordinate system, but they can in the process identify outliers, and you could then remove them or keep them. I'm going to rely on PAM, and PAM is around Medoids, and Medoids are more resistant to outliers. So this is not exactly a completely robust method, but it's a semi-robust method. So I'm going to keep those outliers while building the model. I have to keep it in mind that in the new data, the outliers perhaps should be identified, perhaps eliminated, dealt with separately. But for the model building, I will be happy to keep those outliers. So what we're going to do first we're going to do some experiments to determine how many centroids, or in this case Medoids, we'd like to have in our clustering system. Most of the centroids methods, you need to specify upfront how many clusters you want to get. For that purpose, I'm going to use a small subset of the data. In this presentation, only 100 out of 2000, and create, in this case, 70 clustering systems and measure them using the silhouette measure. What is silhouette measurement? What does it do? The silhouette measurement is applied to every single data point in a clustered system. When the data point is right in the middle of the cluster, the silhouette measure is 1. When the data point is on boundary of its cluster in equal distance to the center of its own cluster and the neighbor cluster, the silhouette measure is 0. If the silhouette measure is negative, it means it's closer actually to the center of the neighboring cluster than its own cluster. So we can then create silhouette measurements not for individual data points but for clusters. So we take the average silhouette measure for clusters, and then we could take the average silhouette measure for the whole clustering system. This is what we see here. Depending on the number of clusters, we calculate the average silhouette measure for the entire clustering system. According to this, it looks like two clusters have the greatest silhouette measure. Okay, it's the optimum. Now, depending what is the business objective, this could be a good cluster number or not. Let's assume we're dealing here with some kind of a services delivered to the owners of those houses in Ames. It could be maintenance services. Perhaps we want to advertise to them. Perhaps we should be able to target certain house types as real estate agents. Okay, so this means that if we consider only two clusters, perhaps we would end up with having big houses and small houses, expensive houses versus inexpensive houses. This may not be good enough clustering. So in some business objectives, this optimum may not be good enough, in which case we'll be looking for other local maximum as other possibilities. For example, the next one would be cluster number 6, and the next one 11, and the next one would be around 21. So I'm going to write them down as possibilities, and perhaps I should be testing them all. Maybe 21 clusters for some business objective is far too many, because it will be difficult to interpret them. We may not have the funds to run 21 marketing campaigns, but perhaps we have enough funds to run 11 or 6. Now, quite often there's other measurements like a gap statistic, and if depending on the data, it could be that all of those methods are not going to be conclusive, in which case quite often people fall into using something called the elbow method. In this case, the calculation for clusters, it's the sum of squares of distances from data point to the Medoid. So this is the within cluster sum of squares as against the complexity of the clustering system, depending on the number of clusters we're going to have. The idea is simple. Can we find such a point, in this case such a k, at which point when we increase the complexity of the clustering system, we don't get a lot of gain in terms of the error or in terms of the measurement of the cluster quality. We can see here there's one point that is like a break with a huge gain to start with, and then it's a smooth line, so possibly around 3 or 4 we could say, yep, here's the elbow. It's a bend after which the gain is much less than before. Perhaps around 21 there's another little bend, but in this case the line is quite smooth, so there's no pronounced elbow. It will be very difficult to use that method. It's a very subjective method, in which case I would rather use silhouette measurements to guide me in this process. So I'm going to pick the number of clusters 6 to start with, and I'm going to develop a PAM clustering system. So let's do it. We have created or segmented or partitioned all the data into 6 groups. It's very simple because all it did, it simply allocated each example to a cluster by creating a new cluster column, and the cluster number has written into it. Each cluster has specific statistics. So we have cluster 1 to 6. They are different sizes. There's no point of aiming for equal size clusters. It may not be possible. The data determines how many clusters is most suitable and also how big are the clusters. We want to avoid the situation we have a lot of tiny clusters, so the clustering system is fragmented. We have some information about silhouettes, the average silhouette width of each cluster, which is the calculation I talked about before. We have also the maximum dissimilarity. The maximum dissimilarity, it actually indicates the distance between, I think in this case is the two between the Medoid and the data. And also we have the maximum, the average dissimilarity. The similarity in this case is measured by Euclidean distance within those clusters. So the average dissimilarity measures diameter is the distance between pairs of points within the cluster, and the separation is distance from the neighboring cluster. We could be using those statistics, for example. Later on, if I want to determine the outliers in the new data, I may look at perhaps the data points which are outside the cluster boundary, as defined as maximum dissimilarity from the Medoid, or perhaps further away from outside the diameter of the clustering system. Just let's look at some other statistics. For each data point, we will know which cluster it belongs to, what is the closest cluster which is a neighbor of it, and what's the silhouette width of that data point. You can see silhouette width for all of them are positive but small numbers, but occasionally you can see that some of the data points are closer to the neighboring cluster than the on-center cluster. If you use k-means, we will not have the situation that silhouette would give you negative values, because the measurement of the middle ensures that all the data points fall into the on cluster. But here, since we use a Medoid, it's one of the points within the cluster. It's quite likely that some of the data points will fall outside the on cluster. Well, here's the picture of the data. I have actually put the cluster column into the data made of principal components, and if I want to rejoin this information with the original data, I can do so by the raw name, which is the identifier shared in the original data set, and this data set in the new coordinate system, and we could actually gain the cluster number in this process. Now the question is this clustering system that we obtain now any good? What's the quality of it? And very commonly what people do, they actually rely on the principal components to chart, they plot the clustering system. So here we have the data. This is exactly the data we're looking at, but we are going to project all of this complexity of data into the first two principal components. So it's a projection. You can see that, and we draw the ovals around, unfortunately, around the means. So, and the Medoids themselves are highlighted. You can see the Medoids are not necessarily in the center of those ovals. That's about 60% of data which those ovals surround. And I'm using my own plotting function from the utility file just to make it simpler. It's very complex. Now, in most of the books on data science, this is it. This is the objective and the ultimate aim of the whole process above. This is quite inaccurate, as this plot, in this case, we know that principal component 1 and 2 explain around 40% of richness of the data, of the variance, which means that in this plot we're missing 60% of data. The data points actually from above and from below have been projected into this plane, so you can see quite a lot of mess. You can see the data points are spread all around, but in other higher dimensions they could be separated. We don't know. You can see definitely that cluster 2 and 3 are well separated. Cluster 2 and 4 we don't know. You can see the data points are intermingled, and in this case, who knows? Cluster 1 and 5, they look like slight overlap, and 2 and 5 perhaps a very large overlap. But that's all we can say. We can't actually interpret it in any way. We often basically look at this plot to actually answer one question. Are centers of the cluster system well separated? The second one is that whether the data is cohesive within their own groups. It's very difficult to say it in this case. We could also look at the higher dimension. So we're going to do the projection of component 1 versus component 3. This is the same data but from above. Because we have here 28 dimensions, so there's a lot of above and above of above. So again, we look at, in this case, even less richness of the data. Its principal component 2 and 3 explain less variance than component 1 and 2. What else we found here? Not much. We only can see that cluster 2 and 4 got separated in a higher dimension. Further away, there's hope in there, but those charts are not useful. So often people look at a so-called silhouette chart. The silhouette chart, it relies on silhouette width, and usually this chart is rotated sort of vertically. Here we show it horizontally. Each of the color areas represent a cluster. Each of the line of those colored areas represent a single data point in that cluster. And the width, the height of that line, it represents the width. And if it's negative, it means that that data point is closer to some other cluster center than its own. You can see cluster 1, very pure. All data looks good. 5, 6 is pretty good. There's very few data items which don't belong to the clusters. But cluster 3 and 5, nearly 50% of data points don't belong there. They're closer to some other cluster centers. It's a very neat chart. It's easy to interpret. And if we have to rely on the data we just produced, the clustering we just produced, perhaps we should think that maybe we cannot trust an interpretation around cluster 3 and 5. Possibly we should remove all those data points. If we want to target some marketing campaign, we could say, yep, we will not target those individual houses in cluster 3 and 5 because we cannot actually trust this clustering system. Let's assume we're going to accept it as it is. Now we're going to very quickly join the cluster information with the original data set. So by the property ID, we retain the cluster number, we rejoin with the original data. And also, since Medoids are the actual data points, I do the same thing for Medoids. If I know the Medoid ID, I can actually rejoin and identify those specific data points which represent the cluster centers. And I reduce the number of variables to be analyzed. Which ones? I picked something that I had a good intuition about. I will also look at how many data points are within each cluster. And this is useful to create the alluvial chart. This is the chart. This is the chart which could be used to tell a story about this clustering system. This is just to give you an idea. I know I can trust cluster 1 and 6. 1 and 6, and possibly cluster 4, maybe cluster 2. So let's talk about 1 and 4 and 2. 2. It's the largest cluster in the system as defined by the band. The band width is obtained from the frequency of this clustering. And what houses are in this cluster? Clusters which have little frontage, very small lot, the overall quality is low, not many bedrooms above ground, so it's a single-story house perhaps. The garage area is small or non-existing. It's older house and sold just a few years ago at the rock bottom price. Let's look at cluster 1. The one we can trust is not many houses there compared with cluster 2, but it's a medium-sized frontage. The lot area is not large, but quality is very high. Again, it's a single-story house, but with a large garage. It's recently built. It sold a few years ago at high price. And if you look at cluster 5, which is orange, it's a larger house on a large block of land. The quality is quite high. It has a few bedrooms above ground. It means most likely it's a double story, but maybe not triple story. It's a decent garage size, not recently built, sold just recently at high price. And we could continue with that. If we select number of clusters of 11, we could still interpret it. If you select cluster 20, this is becoming unmanageable. Okay, so this is a good analysis when we deal with small number of clusters. So what's next? We have developed in the process the model for imputation of missing values, the model for standardization of all variables, the principal component model, and the cluster model. We're going to save them into a disk. And now we're going to test this on a new data set. So very quickly, I'm going to switch to a different notebook. And here, all I do is I use the same packages. So very quickly, maybe I should I'll start from scratch so that not to confuse you. Restart the kernel. So we use the same packages as before. We get the utilities. We load all of the models stored on disk, and now acquire the test data, 930 observations. We do the same transformations. We put IDs as role names, and we select numeric variables only. Now, interesting thing is that we can use the input model which we just brought in from disk and apply it to the test data and eliminate missing values using exactly the same methods before. We do the same with standardization. We scale and center the data in exactly the same way using the same statistics as in training data. Now we will rotate the data using exactly the same rotation method to arrive at the same system of principal components. And I'm going to apply my clustering methods in exactly the same way using the same number of clusters. Now let's quickly verify if we get similar distribution of data. So we have only 900 data points, but you can see that the circles around the new data and around the Medoids from the previous training data, it looks exactly the same. So I have clustered new data into pre-existing clusters. So using the same cluster numbers, the same number of them, and the new data falls into the same systems. Why not actually start anew when you have new data? Because often it's not the complexity of this process which decides whether or not it's a good idea. It is usually the business process which may be expensive to be built around your advice on the clustering and segmentation of the data. It is segmentation of some phenomena in the real world. The policies have to remain, procedures applied, people trained, supply chains organized, and so on and so on, which means that after your advice on the clustering of data, some systems of processes in business need to be put in place, and they hinge upon that clustering system, and the value may have to be returned over the next few months, perhaps, or weeks. If it's an online system, perhaps you could actually rerun the clustering system every day, overnight. Now, I mentioned that with robust methods, we could develop the clustering system with the presence of outliers in the data comfortably. We could have removed them in the process. Now the question is, here we have outliers. We have data points which perhaps have been clustered, put into clusters, but they don't belong there very well. What can we do about it? Can we use the clustering system itself to identify outliers? We can. For example, I can use a global outlier approach, which means that I will try to figure out how many data points are far away from all Medoids. So I'm going to use the sum of squares from Medoids, and if the sum of square is very large, I'll consider that an outlier. I could also use the center, the Medoid, for each cluster, and look at the diameter of the cluster. And if a data point is far away from its center, we could consider it an outlier. So I'll go for the first approach. So I have calculated distances and I standardize them, and if this distance is negative, it's in this case it means that it doesn't mean anything. It's close to 0. It's in the middle of the cluster, and if it's a very large number, I'd say around 2.5 standard deviation from the center, I'll consider that as an outlier. You can see those red dots, those are the outliers in the new data. You can see some red dots in the middle of it, but that's because we have projection into 2 dimensions. If we pick different components, some of those red dots, like from around 0, will move out of the cluster. You can see now we move them out. So depending on your view of the data, you'll see different results. Now, some remarks at the end. Due to robust methods, we have not eliminated outliers, but they need to be detected and eliminated in deployment, as was illustrated here. We have not investigated skewness and sparsity data, which usually affect the PCA, but we could use another library, ROS PCA, which better deals with these issues and also deals with outliers. However, I could not figure out how to apply ROS PCA to new data, so I rejected that for this demonstration. We could have opted for variable clustering rather than PCA, and there's a package called cluster of var, which actually ensures generation of homogeneous variable groups. And so instead of PCA, we could use clustering methods on variables. We need to test different values of k for PAM and decide which one is the best and which one is the best to fit the business objective. And we could use some other measurements of cluster quality, such as RAND index, David-Baldy index, the CCC criterion, or others. There's a lot of scope in there. But for that, I'll leave it with you. If you want to investigate some mathematical properties of silhouette width or gap statistic, which we haven't shown here, you're welcome. And this presentation is actually available on my GitHub, and the link to the GitHub is in the video description on YouTube. So all the best, good luck, thank you for listening to me.